We're on to Unit 7, and in Unit 7 we're covering two ideas, kinetics, chemical kinetics, as well as equilibrium. And they do relate to one another, and that's why this unit is made up of those two ideas. So take some time now, pause, and fill in the main ideas from this paragraph, and go ahead and read this paragraph once, twice, and 3 times. Okay, so as we deal with kinetics, anything with kinetics is rates, and we're calculating what is called average rate. And to calculate average rate is really you're given a span of time and you're given a concentration of your reactants between 2 points. So the reactants may be decreasing with time and the products may be increasing with time, but you're going to see 2 points along that graph, as well as 2 time points, and we're going to take the difference to calculate the rate. And reactants are decreasing, so you're going to put a negative for the difference in the reactants because you're going to see that the reactants are going to, the final amount of the reactants is always going to be lower than the initial amount of the reactants. And so when you take that difference, it's going to be a negative. To counteract that negative, you just put a negative here to end up with a positive rate in the end. Now, rate is essentially the slope of a chord. And so when we look at this graph here, we might make a chord that connects these 2 points, and we're looking for the slope of that. And that's the best that we can do when it comes to rate. We're not finding what is called instantaneous rate. We're calculating the average rate between these 2 time points, okay? So let's go ahead and look at that closely really quick. Later on in the next slide, we're going to be calculating rate from 6 minutes all the way to, I believe, 18 minutes. Yes, 6 minutes to 18 minutes. So essentially what we're doing is we're taking the slope of this line between there, and you're going to, and you'll notice that the slope is pretty close to what that rate is along that graph. So even though it curves downward here, you'll notice that this line is pretty close to being aligned to it, parallel at least for sure, but definitely aligned to it, or close to the alignment of it. Now, the closer we are in the time points, the better our rate will be. Again, this is average rate, so we'll calculate the slope along of this line, of this chord that you see. And if you recall, slope is a change in y over a change in x. And if you look at our graph, that would be our change in concentration over the change in time, because our y-axis is our concentration unit, and of course our x-axis is our time unit. And so that is our slope. You'll need to go back to page 1 for the data chart for this reaction and the data table for the concentration and time units. So let's go ahead and calculate the average rate for each of these substances between 6 minutes to 18 minutes for this reaction. We're going to start off with nitrogen. We're going to calculate the average rate of nitrogen. Now, if you see, there's a minus sign, and so the concentration of nitrogen at 18 minutes is 0.800 molarity. And then the concentration of nitrogen at 6 minutes is 2.00 molarity. And then, of course, notice how this difference is going to lead us to a negative value. And that negative right here is going to counter and make that positive in the end. And then, of course, time is just 18 minutes minusing 6 minutes. Okay? And when you do your math, you will get an answer of, and I'm going to write it down here because I'm really out of room, 0.100 molarity per minute. And you do the same for hydrogen as well as ammonia. And hydrogen, once again, you put a negative and you subtract the concentration of hydrogen at 18 minutes, which is 5.400, minus the concentration of hydrogen at 6 minutes. And I know the time on the bottom is 12 minutes. And you divide your answer and you will get 0.300 molarity per minute. Then you go to ammonia. In ammonia, you're looking at the concentration. This is a plus here. So you're looking at the concentration of 6.400 molarity at 18 minutes, and then 4.00 molarity at 6 minutes. And divide that by 12 minutes, and then you will get your concentration, which ends up being 0.200 molarity per minute. And so notice a couple of things. I'm going to point these ideas out for you to see. The stoichiometry says that it is a 1 to 3 to 2 ratio. Notice that the rates are 1 to 3 to 2 ratio. So it actually follows the ratio. And what I'm going to do to show for that is also this idea of, hey, if this is x, it looks like this is 3x. And this here for ammonia is 2x. And we're seeing that the stoichiometry with the rates align. And that is our answer to this next question. Between 6 minutes to 18 minutes, how do the average rates of nitrogen, hydrogen, and ammonia compare? And we see it that the rates actually stoichiometrically proportion out. So the rates align with the stoichiometry, with the stoichiometric coefficients, which is the coefficients from the balance equation. All right, so you can pause and work on example number 2. You should see very much the same idea as you go through example 2. And the answers are all written right here for you to be able to compare. And you'll notice, again, the comparison with the stoichiometry that you see in this generic equation right here. So go ahead and calculate. The answer keys are, or the key is in red. We're going to move on to the sketching of the graph. So I'm going to start in different, it says to start at a given spot for B, but I'm going to start somewhere different because B is such a low number, and I'm not going to make this an accurate graph. It is a sketch. Molarity is in, or concentration is in molarity, and the problem is the time unit actually is in seconds. So I'm going to start off with my B. Well, actually, I'm going to start off with A because A has a coefficient of 1. It's good to start at the lowest coefficient. And you can start anywhere for A. So this is my black color is my A. And because it has the lowest coefficient, it's going to decrease the slowest compared to the others. Then I'm going to move on to my other reactant, which is B. I'm going to make B green. In B, I can start anywhere along the y-axis, but I have to have some. And I'm going to see that B is decreasing a lot sharply compared to A. I hope that shows for the sharpness. If it's parallel, then it probably doesn't. So I'm going to change that up a little and redo that spot. So a lot sharply means, there, that's more sharply. or twice as sharp. And you're approximating, so this is B here. Now we go into C and D. C and D is going to be 3 times that of A, so it's going to be even more of an increase. So C starts at 0 because it's a product. And when I show for C, I'm going to see it move quite even sharper than B. And then, of course, D, my last one, is also going to start where C starts because it's a product. And you're going to see even a sharper slope. And I like being able to use the C as my reference for how I'm going to draw D, because D is going to be even faster. So you can see that the slope along here is sharper than the slope right here along for C. So you're comparing C to D pretty nicely. And so those are that's a sketch of all 3 substances in that reaction. We are going to ask ourselves, do all collisions among reactants lead to the formation of products? And that leads us into what is called the collision theory. Of course, we describe those collisions that lead to the formation of products as effective collisions. And of course, I say not at all. There are 2 factors that are required for an effective collision to occur. The first one is that reacting particles must have a minimum amount of energy called activation energy. And secondly, reacting particles must have the correct proper orientation while colliding to be effective. Let's explore both ideas. I have a video to help us to understand activation energy, and it actually brings us back to this energy diagram. So let's watch this video. So here's an energy diagram. It's our potential energy diagram. And we're going to be looking at 2 reactants, A squared, it's a diatomic molecule, B squared, another diatomic molecule. And they're reacting to form 2AB. Now we're testing to see if all collisions lead to the formation of products. So we're going to test it out with low kinetic energy. So these particles are going to have low kinetic energy to start. And then we're going to test another scenario where they're high kinetic energy. So let's see what happens in low kinetic energy. So we're starting at the reactants on the energy diagram. Now, upon seeing them collide, you'll see them collide very slowly because they have low kinetic energy. And the particles bounce right off each other unchanged, which means the particles do not form, that collision did not form products. So it's an ineffective collision. Now, you notice that those reacting particles were moving up in potential energy, but they couldn't get over the activation energy. So there wasn't enough activation energy to form an effective collision. Now let's see what happens in the second scenario. High kinetic energy. Those particles are moving much faster, and we did overcome the activation barrier, which is called the activation energy, leading to the formation of products in this case. And you'll notice change particles. Now you have 2 AB particles. So the reaction or the collision there was effective in the end. Summarize what you have learned from this part of the note video on the potential energy for a scenario where there's high energy reactants versus low energy reactants. Now, aside from the activation energy needed, we also have to have, and this is an and statement, proper orientation. So you have to have both in order for a collision to be an effective collision. So let's talk about proper orientation. So here you have a scenario, a reaction, and there's 2 possible collisions. There's one collision that is effective and the other one's ineffective, and we'll talk about why. If you have A squared or A2 here lined up parallel to B2, when they collide together, notice how you can actually make 2 ABs pretty nicely and easily from that. So again, once you form your activated complex, this is your activated complex. Notice there's more bonding, and so it has a high potential energy. Now you form your products. Your products is 2AB. So this collision will lead to the formation of these to the formation of the products, which is 2AB. Whereas this collision, where they're perpendicular to one another, you're not going to see them lead conducively to 2ABs. And so that's why you're seeing this reaction reform to form the reactants back again. You won't see new products forming. And so this is an effective collision. This is an ineffective collision. I'll write that in just to be sure. So this is effective, and this is ineffective. So now how do we help these reactions lead to effective collisions? How do we in some ways manipulate the activation energy or the orientation in such a way as to encourage these reactions to be effective? There are 5 ways. There are 5 ways that we can manipulate, and they're all things that we can do in the laboratory condition-wise in order to speed up their reaction. And one of them is concentration. The next one is the reactivity of the reactants, temperature, and then catalysts and surface area. And oftentimes we will manipulate several of these 5. You're not just strictly looking at one at a time. You're actually manipulating several of these 5 different ways we can speed up a reaction. We're going to look at 5 factors that increases reaction rates. And really they all will lend themselves to helping with allowing these collisions to be effective collisions. So the first one we're going to go over is concentration. If you notice at the beginning of a reaction, the rate is really fast. And it's really fast because you have a lot more concentration of the reactants available to react. And so that is describing how the increase in concentration will lead to a faster, quicker reaction. And that's what's happening initially. And then it kind of levels out afterwards. So it slows down at the tail end right here. Temperature. The animation that we saw last time, or last slide, really deals with temperature, because when you increase the kinetic energy is determined or defined as average kinetic energy. So the higher the kinetic energy of these particles, the more they will meet the activation energy needed to overcome the activation barrier and form products. So high kinetic energy particles oftentimes led to the formation of products, and then low kinetic energy did not, because you didn't meet the activation energy. Now we go to surface area. I wanted to show you something that you could apply to in real life. When you start a fire, you usually start a fire with kindling. And kindling is this small little shredded pieces that have high surface area versus fire log or firewood. Firewood is outside of that. And normally you start a fire with kindlings because they start up really fast. They burn really fast. And so we find that things with higher surface area will burn faster than the firewood that's outside of that in the end. And it is no different with cube sugar versus granulated sugar. Cube sugar will dissolve much slower than granulated sugar. Let's go to catalysts. Catalysts. What a catalyst does is a catalyst added to a reaction is going to lower the activation energy. So what it does to this endothermic potential energy diagram is it lowers the activation energy, as you see here. So this is an added catalyst. Now how it does that is what we're about to see in this animation, that video that I'm going to play. So let's watch. We are going to understand how a catalyst is able to lower the activation energy of a chemical reaction. And so the catalyst that you see right here is platinum. It's a piece of metal, and it's a solid piece of metal that is a surface for which your reactants are going to be drawn to, and that will then lower the activation energy for the reacting particles that would be needed in order to overcome and become products. So I'm going to play this out, and you're going to notice exactly what I just mentioned, how the reacting particles A squared and B squared are going to be attracted to this platinum catalyst, and that's what's going to lower the activation energy. So A squared is drawn to platinum. And notice how A squared and B squared are not colliding with the same kind of energy that's needed to get through the activation barrier. It's because now we have platinum as a surface to draw those particles together. So that's how we're lowering the activation energy. Now the catalyst does not get used up. So you'll notice that platinum was never in any way degrading as this reaction takes place. It just is as it originally is, without any use or reaction with the reactants. So catalyst, however much you take of it, is not going to be used up. Now, this idea we cannot manipulate so much, but we can if we can substitute different reactants, we actually can increase the reaction rate by the substitution of certain reactants that are more reactive. And so let's go to the alkali metals. We know that alkali metals are increasing in size as you go because there's more energy levels as you go downward on the graph or on the periodic table. And so with that increase in energy levels, you're actually going to see that metals which like to lose electrons are going to have an easier time, and they're going to be more reactive as you go downward. And that's why rubidium in water, if you put it in water, is going to be more reactive than lithium in the end. Okay, so rubidium is going to react faster than lithium. So that goes over all 5 ways that we can actually enhance and allow these collisions to be more effective collisions, increase the frequency of those effective collisions. We're jumping into equilibrium now, so let's go ahead and pause the video, go ahead and fill out this paragraph, which by the way continues on the next page. So fill out the blank spots. These are the main ideas going into chemical equilibrium. Read it several times, and we'll move on to the next page once you've done so. There is a wide variety of different equilibrium constants, and Ksb as well as Ka, Kb are the only ones that we will look at in our class. We won't go into Kp. You'll do that next year if you go into AP Chem though. So Ksb is basically salt, ionic salts, and you're making a saturated solution, which is a solution that is in equilibrium between the salt, the solid salt, and the 2 ions, cations and the anions that make up that salt. So to write the reaction for any kind of Ksb reaction is to start off with the salt, and I'll just do I'll do the first one listed on the Ksb chart, which is barium carbonate. And so it starts off with BaCO3 solid, and it's again always the solid ionic salt. So there's your ionic salt. And then it's in equilibrium. So again, the equilibrium symbol is this double-headed arrow, and the 2 ions that make up this barium carbonate, including barium and carbonate. And so this is what a Ksb reaction looks like all the time. Again, the cation, and the anion is in the product side, always. Likewise, for acids, I'm just going to sketch out what an acid would look, or an acid equilibrium reaction would look like. And it always starts off with your acid. Let's start off with the first. Actually, we'll do they're all strong. The first one listed, the first few ones are listed are strong. Let's do nitric acid. Or let's do or hydrofluoric acid. That's an easy one. So hydrofluoric acid, and acids are aqueous. So we always start off with the aqueous acid, and then the two ions that make up the acid are hydrogen and fluoride ions. And that there is, in fact, your equilibrium reaction for an acid ionizing in water. We don't put water in there, but if you may if you'd like to, but really we try to just singly look at the species that are relevant. And water is a pure liquid, and you're not going to see it part of the equilibrium. A reaction that goes to completion would look like this, and what makes it distinctly a reaction that goes to completion and one directional is the fact that one of the reactants, which is called the limiting reactant, will zero out. So A is going to you're going to see it decrease, the amount of concentration of A decrease until it zeroes out. And B is going to increase until A stops. And when A stops, the rate is going to flatten out like you see here. Whereas in equilibrium reaction, you'll notice that both reactants and products, both A and B, are not going to, neither of them are going to zero out. So you're not going to see a limiting reactant. And I'm going to graph that so you can see the to contrast. So A is a reactant, and so you're going to start off somewhere along that y-axis on top. And A is going to be decreasing with time. B is going to increase at starting at 0. It's going to be twice as fast of an increase. So I'm going to see twice. And so where you reach a point called equilibrium is when you see that they both level out. And so I'm going to redraw B so that we can see it leveling out a lot better. Okay. And where that occurs is called equilibrium. And I'm going to, and I see them constant. The concentration of both A and B are constant at this point. And so this is the start of equilibrium. And it continues from there on out until it gets disrupted or stress. And that is the stress that we're going to address are stresses that apply to Le Chatelier's principle, which we'll discuss later. So here what you're going to read is the equilibrium story, and you're going to graph that equilibrium story, and you're going to pay attention to the stoichiometry, so the 1:3:2 ratio. And I'm going to go ahead and work that out as well. So here's my time unit and my concentration unit. So this is my time. And of course, I don't have room on the left side, so I'm going to say this is my concentration unit, okay? And I'm going to graph both nitrogen. Nitrogen in my original graph from the beginning of the unit was blue. And I'm going to start right here, and it's a sketch. You're going to see nitrogen start off decreasing very slowly, and then it peters out. And then, of course, you get to hydrogen. Hydrogen, I believe, was in red. Now, taking a look at graphs A and graph B, you'll notice that when you hit equilibrium, which is right at this point right here where the dotted line is, you'll notice the reactants and products are not equal. Same right here. It's not when they cross each other that equilibrium occurs. It's when the reactants and products stay constant, and it's this point right here that you see equilibrium to occur. the neat thing about the fact that the reactants and products remain constant over time is we can ratio the products over the reactants and lead to a constant an equilibrium constant, and we call that KEQ. Now, these brackets represent molarity concentration. So just a reminder, it's molarity. And X and Y represents the stoichiometric coefficient. So if you have a reaction that's generic like this, to write the expression for that reaction is to put the products on top in the numerator, raised to their stoichiometric coefficients. So notice how Y is the stoichiometric coefficient for product C, and Z is the stoichiometric coefficient for D. So you're raising each of the reactants and products, or products and reactants, to their stoichiometric coefficient. Now, what does KEQ tell us? It tells us equilibrium, what's happening at equilibrium. But what if the constant ends up being a number that's greater than 1 versus equal to 1 versus less than 1? Well, it tells us what we have more of at equilibrium. So if your products or if your KEQ is greater than 1, that means there's more products at equilibrium. And that happens because the numerator is the products. If you have a higher numerator than denominator, you're going to see a number greater than 1. If they're equal to 1, that means that neither one or the other is actually favored. You're seeing them equaling. So products equals the reactants at equilibrium. And so that's why you're seeing that equal to 1 in this case. If the KEQ is less than 1, that means there's more reactants. So there's a favorability on the reactant side at equilibrium. And so that's why you see there's more reactants than products. And so the KEQ is going to be less than 1 as a result. Now we're going to practice writing expression. So all expression is products over reactants raised to their stoichiometric coefficient. However, we are going to make sure we are aware of one big idea, which is solids and liquids do not impact equilibrium, as you read earlier in the paragraph. You read that solids and liquids have a constant concentration, so they will not impact equilibrium at all.
So the question is, why do solids not affect equilibrium? So right now, the system that you see in here in this vessel is at equilibrium, and you know it because you see that the 5 gas particles or carbon dioxide molecules that you see floating around stays at 5 over time. So in other words, it's 5 right now. 10 seconds later, it's still 5. So it's actually staying constant. The concentration of that carbon dioxide is staying constant over time. Now, you also notice some calcium oxide as well as calcium carbonate. That's in green. Calcium oxide is in orange. When I add, and by the way, this system's at equilibrium, and aside from the concentration, there's an error on this. There should be a double-headed arrow. So imagine the arrow going the other way as well, the reverse direction. As I add more calcium oxide, watch to see what happens. Does that change the amount of carbon dioxide? It's still 5, right? So it looks like adding more solid to a system that's at equilibrium has no impact on it. So if I add more or take away, you're going to see that it's not going to impact. Likewise, for calcium carbonate, which is also a solid, so these two are solids, you're going to see that it has no impact on the system. And you would see impact if you saw amounts of carbon dioxide changing. Adding more did not do anything. Notice adding more calcium carbonate didn't change the amount of carbon dioxide. So hopefully the takeaway is knowing that solids added to a system at equilibrium is not going to impact that impact that equilibrium system.
Finish all the rest of the problems from B to D. Also notice that The K could be KEQ, KC, C stands for concentrations, and they're all in concentration units. And then there's also K, where you don't see any subscripts. That could also be, that will also mean equilibrium. And so it's anything with a capital K, and again, it could be KC, KEQ, or just plain old K. Check your answers and make sure that you understand why you eliminated all the solids and liquids, and of course raising each of the reactants and products to their corresponding stoichiometric coefficients. In example 2, you see that you're given equilibrium positions for this reaction, this equilibrium reaction right here, between carbon monoxide, hydrogen, methane, to form methane and water vapor. So if you look at this, these are experiment 1 and 2, and these are all concentrations at equilibrium. EQ means equilibrium, and they're all in molarity concentrations. I'm going to show you that even if we started off with a different set of equilibrium concentrations, and then we do the experiment again and lead to a different other set of equilibrium conditions, that the K constant will be the same in the end. So we first start off with our expression. Our expression is products raised to their stoichiometric coefficient over reactants raised to their stoichiometric coefficient. Watch for hydrogen. Hydrogen's stoichiometric coefficient is 3, as you see here. So we go ahead and look at experiment 1, and we plug in the products over the reactants raised to their stoichiometric coefficients at equilibrium. And because this is the equilibrium constant, we want to make sure we put these concentrations that are at equilibrium. When we divide it, or multiply and divide, or raise it to the Q power as well, you're going to see 3.99 as your final answer. Likewise, when we do this for experiment number 2, we also see that 3.99 or 3.933 is our final K constant. Notice how the two experiments, as long as we're at the same temperature, will yield the same constant in the end, 3.933. Now, based on the constants for experiment 1 and 2, experiments 1 and 2, is the reactants products are neither favored at equilibrium. So if your constant, your K constant is greater than 1, as we see right here, 3.933 is in fact greater than 1, that means there's more products than reactants. And so that's why your KEQ is greater than 1, which means because there's more products, that means more products is favored at equilibrium than the reactants. Let's go ahead and work through another equilibrium problem. This is actually what you're going to see more often. And oftentimes in an equilibrium problem, we ice it. We use an ice table. In the ice table, you'll notice that E doesn't stand for end anymore. It actually stands for excess, or equilibrium. Nor does it stand for excess. So it actually stands for equilibrium. So let's go ahead and take a read. I would pause this video and read this question a couple of times just to make sure you know what you're trying to solve for. Okay, after reading this problem, you'll see that your initial amounts are going to be placed in the ice box for both the reactants and products. So it looks like you're given 0.200 moles of your dinitrogen monoxide, and that is a reactant. Now it's given in moles, and we know that equilibrium is in molarity. So these brackets represent the molarity concentration. So I need to find out if I could, or find out what the volume is. And the volume looks like it's 10 liters. So I'm going to take moles divided by liters to get my molarity. And in doing so, I get an answer of 0.0200 molarity. I do the same for oxygen as well, and I find out that I get 0.0560 molarity here. And it says that we're placed in a vessel, and obviously there isn't any products to start. It doesn't say anything about the products, so we're starting the reaction initially. A change occurs. Now, how I know what the change is by the information given to us. And it says right here that at the end, when equilibrium is established at 25 degrees Celsius, the amount of nitrogen dioxide is found to be 0.2 moles. So the amount of nitrogen dioxide. This is nitrogen dioxide. This is the equilibrium amount. So we're going to put that value in, of course, converting it into molarity first. And when I do that, I get 0.0200 molarity. Now, which means our change. Let's go to our change. We know that from the change that you see here, when it started off with 0 and now it ends up with 0.0200 molar, you know that you've made 0.0200 molar. In other words, plus, this is a plus, which means you lost these reactants amount, and it has to be stoichiometrically proportioned. What do I mean by that? Well, the amount that I lose of this is going to be half whatever this value is. So because it's a 4 to 2 ratio here, or 1 to 2 ratio, so it is going to be half. So whatever this value is, half of that is going to be 0.010 molar. Now, 2/3 that amount is what your, or sorry, 3/2 of that amount is what this, 3/2 of this amount is how much of this oxygen reacts because of the 3/2 ratio. So basically 1.5. 3/2 is 1.5. So 1.5 times 0.0100 is in fact 0.0150 molar. And so now you can subtract and get your final equilibrium amounts. So this is going to be 0.0100 molar, and this is going to be 0.0410 molar. And if I write the expression, so I'm going to take a little time to write the expression so I know what I'm substituting and what I have to raise power-wise. So this is going to be nitrogen dioxide raised to the 4th power. I'll put the raising later so I can color code that. N2O, and then also O2. So these are the products on top, reactants on the bottom. And I'm going to raise them to their stoichiometric coefficients. So the stoichiometry here is 4th power. The stoichiometry here is 2nd power, and then this is 3rd power. So then I just multiply all those raise them to their powers. So equilibrium is equal to the products, which is 0.0200 raised to the 4th power, and then the reactants, 0.0100, which is dinitrogen monoxide, raised to its power, and then of course the other reactant, which is oxygen, raised to its power. So this is to the 4th power, this is to the 2nd, and this is to the 3rd. And when you solve it, you should get your final answer. An equilibrium constant, the actual constant itself, is never an actual value. So your final answer is 0.2, or sorry, there's no units. What I mean by that is there's no units to the final answer because of the different powers that you have to raise it to. You're not going to see a consistent unit for every equilibrium constant. So the answer is 0.232 in the end when you solve for KEQ, solving this problem. Let's go to the next problem and let's explore how to do that. The next problem is another equilibrium problem, but now it's KSP. So you're looking at KSP, which is solubility product equilibrium. So it's dealing with the ionic salt and the dissolving of that ionic salt to make a saturated solution. So the problem says, what is the molar solubility and concentration of the cation and anion at equilibrium? So we have a lot to do. We're trying to find the molar solubility. And I'll talk about what molar solubility is in a second once we go through this problem. It's a very straightforward definition for what it is. It's the solubility for a mole of that salt in the end. Okay, so to start this problem, I have to go back to page 5 and refer to the table of constants, solubility product constants. And I'm going to look up silver carbonate, and I have to find out what that value is for silver carbonate. It looks like, when I look it up, the KSB for silver carbonate is 8.5 times 10 to the negative 12 on that chart. Okay, here's my equation. My equation is always going to be the solid and, of course, dissociating into the ions that make up that solid. So 2 silver ions and 1 carbonate ion. I then do my math and I notice that I start off with basically 0 of my reactants. I don't have any reactants. And I really don't care how much I have of my reactants because I'm figuring out how much I add of my salt, my ionic salt, to make a saturated solution. Now, why do I not care about this here? Sorry, I put 0, but really I don't care about this, the reactant. And I don't care about it because it's a solid in the end. Notice the word solid right here. So I'm going to cross it out for both the equilibrium as well as initially. Now the change is really how much I'm going to dissolve of that salt to make a saturated solution. So I'm going to lose some of this. I'm going to dissolve some of it, and I'm trying to solve for that molar solubility because it says calculate the molar solubility up here. And I then know that I initially have 0. I have pure water, nothing of the salt. I'm going to dissolve some of that salt, and when I dissolve some of that salt, I'm going to make twice, however many moles that dissolved of this is going to be twice as much. Why? Because it's a 1-to-2 ratio. And then the amount of moles of carbonate is going to be X amount because, once again, it's a 1-to-1 ratio. So however much for every 1 mole of this, I'm going to form 1 mole of this. So it's going to be proportional or ratioed out stoichiometrically. My equilibrium amount is super easy. I just say X and 2X, and then I write the expression. It's always important to write the expression. My expression is products raised to its stoichiometric coefficient, as well as the other product, carbonate ion, raised to its stoichiometric coefficient. And notice that this is a solid, the reactant is a solid, so it's not to be included in the equilibrium expression. And from there, I'm just going to solve. And I can actually solve because you'll notice that you'll have an unknown variable, one unknown variable, as you solve. And so the concentration at equilibrium for silver is actually 2x, and you have to raise that to the second power. The concentration of carbonate is x, and you have to raise that to the first power. And if you simplify this side, you'll notice that you get 4x squared times x, which means I get 4x cubed. And of course you have to first get rid of the 4, so divide both sides by 4, and then you're going to have to do a cube root. So after you divide by 4, then you solve for x. And x ends up being, the final answer ends up being right here. Right here. This is the molar solubility. So 1.29 times 10 to the negative 4th is your final answer for the molar solubility. Now, which is this x right here. If you know what X is, you then double it to find your concentration of silver at equilibrium. And then the same X is going to be the concentration of carbonate ion at equilibrium. Okay, so that's why this is 1.29 times 10 to the negative fourth, because molar solubility is going to be the same, however much of the salt that dissolved for 1 mole of it is going to be however much the carbonate ion that will form. So that's why they're the same values. X here. Twice X is this number right here, and that's silver ion concentration at equilibrium. Equilibrium can also play out in an acid, a weak acid, or a weak base situation. So this is a weak acid situation. That's why we have something called the Ka. A stands for acid. And let's go ahead and look back to page 5 so we can find the acid, nitrous acid, and there we can then use that constant to solve for our equilibrium concentrations. So let's go ahead and begin. Your Ka, when you look it up, is in fact 7.2 times 10 to the negative fourth for nitrous acid. So this is HNO2. Now, if you look at the reaction is the ionization of the acid into the two ions that make it, which is the hydrogen ion and the nitrite ion. Okay, so those are the two ions that make up nitrous acid. So let's go ahead and figure out the equilibrium amounts using the equilibrium constant. Equilibrium constant helps us to understand equilibrium amounts here and the ratio of that. So let's begin. We start off, we're being told that you have this concentration initially of your nitrous acid. So we're going to put that into our initial amount. Of course, you don't start with any products yet because it hasn't ionized yet. And so when you ionize nitrous acid, you're going to you don't know how much ionizes, so you're going to call that X. So you're losing some of that. You're making this amount X as well as X here, and they're all stoichiometrically ratioed. What that means is, notice this is a 1 to 1 to 1. This is 1x, 1x, and 1x. So they're all stoichiometrically ratioed. We really want to know how much is going to ionize of this acid. Okay, so X is going to be the amount ionized specifically of the original acid. So this is your original acid before it's ionized, and so this minus X right here is how much ionizes. So at equilibrium, in this case for an acid, because your acid is aqueous, it's going to count in the equilibrium. Unlike solubility product, which was a solid, it wouldn't count. Because it's counting, we have to put that in the equilibrium box. This is X and this is X. So now we write the expression. We always write the expression out so we know what we're substituting and what we have to raise to what power. So this is H plus ion, and this is nitrite ion. And of course, we're going to have to include nitrous acid in this equilibrium because it's aqueous, and they're all aqueous, so they're included in the equilibrium. So now that we know our equilibrium concentrations, so E, we have all our E, we're going to substitute it in each of these. The hydrogen ion concentration is X. The nitrite ion is another X, so X times X. Likewise down here, it's 0.10 minus X, so that's what we're going to place down here at the equilibrium concentration. And we're going to substitute all the values as well. So we're going to squeeze in 7.2 times 10 to the negative fourth equals, we're taking X times X over 0.10 minus X. Now, this is a hard problem to solve. This is going to lead to what is called a quadratic formula because we have X squared right here. We also have x to the first power, and then we also have a constant, x to the 0 power. So it's going to look like your typical quadratic formula where it's ax squared plus bx plus c equals 0. So it looks like that kind of formula when you rearrange this equation and simplify it any further. But we're not going to go there. We're not going to solve using the quadratic formula. That's a little bit too much work for us. We like to use something called the assumption method. So we're going to assume that x is very, very small compared to 0.1. And if it's very, very small compared to 0.1, we can say that this x, since it's so small compared to 0.1, it is going to be 0. So basically, this term right here is going to be just 0.1 instead of 0.1 minus x. So we're going to correct this term to be just 0.1 because we assumed that x is very small. Now with that, we can now solve for x with a lot more ease. In other words, we're left with x squared, and then if I multiply the 0.1 over to the 7.2 times 10 to the negative fourth, so I'm going to get 7.2 times 10 to the negative fifth when I multiply that over. I then can solve for x, and x will be the amount that ionizes. Okay, so click on your get your calculator and make sure that you see the math behind all that. Okay, and x, when I square root it, x ends up being, and I'm going to write it in here because I'm out of room. So x ends up being equal to 8. I'm going to square root that. 8.48 times 10 to the negative third. So 8.48 times 10 to the negative third. So that's the amount that's ionized as stated up here. X is the amount that ionized, and this is the same x. So now how do we calculate the percent ionization? It's a very easy equation. You take your x, which is the amount that ionized, and you divide it by the original concentration. The original concentration is 0.1, as stated right here. So then you just calculate the percent from there. So it's a very simple equation. So percentage equals, you're taking 8.48 times 10 to the negative third, and you're going to divide it by 0.1 and then times it by 100, and that will give you your answer, which is 8.49%. Now let's move into Le Chatelier's principle. So we all understand what equilibrium is and how to calculate concentrations at equilibrium using this ICE table. It's a very nice table to set up anytime you have an equilibrium problem. Now we're going to learn about stresses on systems that are at equilibrium. So I would like you to pause the video and take all your key words into this description of Le Chatelier's principle. Okay? Just think to yourself, do the opposite of the stress. So from here on out, you'll hear me say undo or the opposite of the stress. So there are 4 types of stresses that you're going to see, but really it's 3 types. And the 3 types of stresses are, there's an effect on concentration, there's pressure and volume, which are, by the way, inversely related to one another, and there's also temperature. So, and effect on catalyst. But catalyst has no effect, and so that's why I don't really count this as an effect. But we'll talk about each one, and we're going to see the specific stresses on this system that's at equilibrium. And we're going to make sure we undo all of those stresses one by one as we go through it. So here's a system that is at equilibrium. I know it's at equilibrium because I see that double-headed arrow. And so as I add more nitrogen, concentrations of nitrogen to the system, what does this reaction want to do? It wants to consume that nitrogen. So it wants to get rid of the nitrogen. How do I consume the nitrogen? Well, I got to go this way. I got to go forward in order to consume this nitrogen to make nitrogen dioxide. Okay, so you're going to see for that example that the shift is going to be a forward shift. Now, again, forward shifting, going this way, or going forward, which is this direction, is going to consume the nitrogen that is the stress. Now, let's go and see what happens if we add more O2. Adding more O2 is going to do just what you did here with nitrogen. It's going to cause the reaction to move forward. Moving forward will get rid of nitrogen quickly. And so, by the way, I do want to stress what that means. Moving forward means if you're going through a forward shift, that means the forward reaction is going super fast. Even though there is a reverse reaction, the reaction is also going reverse, but the forward reaction is going very fast until the forward reaction equals the reverse reaction, which means you've reestablished equilibrium at that point. So let's go ahead. Again, adding more O2 is going to forward shift. Now, adding more nitrogen dioxide, on the other hand, adding more nitrogen dioxide is going to shift the equilibrium going reverse because it wants to get rid of the nitrogen dioxide. And the reverse direction, if I speed it up in the reverse direction, that will quickly get rid of the excess nitrogen dioxide until you reach equilibrium again. Once again, you're always trying to get back to equilibrium when you stress the system out. And the new equilibrium state is actually a new state in equilibrium. It won't look like exactly the same as the equilibrium state before the stress. So it's going to be a new established equilibrium. But the constant is going to be the same constant value. So the ratio of products over reactants is going to be the same constant value. All right. So now we go into stresses dealing with pressure and volume. When it comes to stresses dealing with pressure and volume, the higher the pressure means the lower the volume. That means they're inversely related. So vice versa, lower pressure means higher volume, or the other way around. So this is an inverse relationship between the two, okay? Pressure and volume. Once again, we're looking at stresses on a system that's at equilibrium. So here is the first scenario. The first scenario is when the moles of the reactants does not equal the moles of gases in the product. Now, why are we counting moles of reactants and products? Because pressure is only for gases. And so pressure exerted is going to be impacted for gases only. Think about this. If I had a bottle of water, I add more water to it, is that going to change the pressure above the water, the vapor pressure, in other words? No, it isn't. But if I add more gas into that bottle, it actually is going to change the amount of gas or the pressure that's in that bottle, because gases are the ones that can collide against the walls of the container to exert pressure. So that's why we have to count moles of gases. So in counting our moles of gases of our reactants and products, so I'm going to count total moles, okay? I see here 1 mole of nitrogen gas. I see 3 moles of hydrogen gas. So what does that total us to be? 4 moles of gases. Let's go to the product side. In the product side, we see that there's only 2 moles of gases. So if my first stress here is to increase pressure, which means, in other words, I'm decreasing the volume. Think about this for a second. If I'm decreasing the volume, I have less room now. So where would I want to go? I want to go to the less moles of gases. So it's going to be a forward shift. Forward shift. Once again, just to remind you, if I have less moles of gases, or less room that I see here, or I want to find a way to decrease pressure, the only way to decrease pressure is to move to the side with the less moles of gases. And so my shift is going to be a forward shift. the opposite, where I'm increasing the volume, giving me more room and thus lessening the pressure. Now my system wants to try to increase pressure by going towards the more moles of gases. So this is going to be a reverse direction shift. So the reverse direction is going to move fast until it reaches equilibrium. And at that point, the forward and the reverse rates are going to be equal. So now we go to the next scenario. The next scenario, we're actually seeing that the moles of reactants is equal to the moles of the products. So let's count it. Here I see 2 moles of gases in the reactant, and then I see 2 moles of gases in the products. So these are all gases that I'm counting. And in that case, when I stress the system out, it's going to the reaction isn't going to find a way to shift it in any direction more so. In other words, it's going to be a complete stress on the whole system, and you're seeing that the reaction can't compensate for that, undo that stress. And so there's going to be no change as a result. In both scenarios, no change. Now we're going to look at some animations to help us to understand how pressure and volume will impact a system that is at equilibrium.
Is at equilibrium, and technically there should be a double-headed arrow right here, so there's a little bit of an error. If you count how many particles there are in this container, gas particles that is, you'll see 6 nitrogen dioxide molecules roaming about, and there should be 2 dinitrogen tetroxide molecules roaming about. So count it and you can see it from the modeling. I'm about to compress this container. When I compress this container, we're going to see less volume, less room for these particles to move. And so their equilibrium will find a way to shift in order to compensate for the less room that you have. And so let's look to see what the shift is. You'll notice that there are now more dinitrogen tetroxide. There's 2 more, and of course there's 4 more is lost of the nitrogen dioxide. So there were 6 initially, 4 of them were taken away to make two of the dinitrogen tetroxide. And why that happens is because there's less room. Where there's less room, the equilibrium reaction is going to move towards the side with the less moles of gases, which is dinitrogen tetroxide. So for every 2 particle, you're going to be forming 1, and it's going to move quickly to form 1 so that it can compensate for the less room that you have inside this container. If I expand, you'll notice that the particles will go back to where it originally was, which is 6 particles of nitrogen dioxide and 2 particles of nitrogen tetroxide. When I compress, once again, you'll see the particles, 4 of the nitrogen dioxide decreasing to make 2 of the dinitrogen tetroxide. And we are reestablishing equilibrium, and how we know is as time passes, you'll see that the amount of reactants and products remain constant over time. So let's go ahead and look at another different scenario, so another reaction. In the second reaction, you're going to see, once again, the error is the arrow, you're going to see 2 moles of you'll see the reactants, which is the yellow ones are the hydrogen, diatomic molecule. Purple are the iodines. And there's 2 hydrogens and 2 iodines. And of course, you also see some products, which is the Hi particle, gas particle. And there's it looks like there's 2 of them. So notice 2 of everything, 2 hydrogen, 2 iodine, and 2 hydrogen iodide particles as gases. Now I'm going to compress, and when I compress, you're going to see if there's any changes in the amounts of both hydrogen iodine and hydrogen iodide. So let's count. You see 2 hydrogen molecules, you still see 2 iodine molecules, and you still see 2 hydrogen iodide. Now,
upon compressing, what you've done is you've changed the volume. Thus, you increase the pressure inside the system. But because there's 2 moles of gases on the reactant side and 2 moles of gases on the product side, you're not going to see this reaction try to compensate or the shift occur according to Le Chatelier because they have the same number of moles of gas particles. So the reaction doesn't know where to go to try to compensate for equilibrium. So it looks like this whole reaction, this whole system is going to increase in pressure one way or another, and the reaction can't compensate for or will not shift forward nor reverse in order to try to reach equilibrium again. Let's continue on with temperature stresses. So we're looking at temperature stress. And when it comes to temperature, we're looking to see if the reaction is endothermic or exothermic. So we're going to have to put heat on the right or left side of the reaction depending on if the reaction is endo or exothermic. Accordingly to what you see in this first reaction, this first example, you're looking at an exothermic reaction because your total change in enthalpy is negative. So you're going to put your heat on the product side. On the other hand, if you look at this reaction, the total change in enthalpy is positive, which means it's endothermic. So you're going to put heat on the reactant side. When a stress is applied to an exothermic reaction, you're going to see, depending on what the stress, temperature is increase or decrease, you're going to see the reaction either shift forward or reverse depending. And so let's go ahead and take a look at this reaction and what would happen if you shift forward. If you shift forward, you're producing more heat. If you shift reverse, you're absorbing that heat. So it's exothermic going in the forward direction, endothermic going in the reverse. So if you increase temperature as the first stress is stated here, you're going to try to undo that stress by decreasing temperature. Decreasing temperature means you're going to have to absorb that heat. And absorbing heat means you're going to shift reverse. So the answer to that is shift reverse. And then the opposite is true, where you're going to shift forward because you want to try to increase the heat from the stress of decreasing temperature. In order to increase heat is to go in the exothermic direction, which is the forward direction. Now let's go down to the endothermic reaction. Heat is on the reactant side, as you see right here. And so if you increase temperature, you're going to find a way to try to absorb that heat. So you're right to say you're moving forward. So you're moving forward to try to absorb that excess heat. And then, of course, if temperature is dropped, you want to move in the exothermic direction, which means you're going to go reverse as a result. Adding a catalyst speeds both the forward and the reverse reaction likewise, and because you're speeding the forward and the reverse reaction, adding a catalyst will have no effect on the equilibrium, so there's no change on the equilibrium system. I would like you to pause this video and work through all of these problems, making sure you notice everything that's given to you as you go through each example problem. I'll have the answer key after you pause. So here's the answer key. The one thing to note is the answer for letter D, and realizing that the stress that you've done is you've added lead 2 sulfide, which is a solid, and we know that solids do not impact equilibrium, so that's why it's no change here. And that's really the big one that might be overlooked by students. So the only new thing about this example problem is this category that says effect on quantity and its effect. So you're seeing what happens when you stress the system, the direction it will shift, and then as a result of that shift, what will be the effect on ammonia, whether it's going to increase or decrease. Okay, so we'll do one or two example problems, and then I'll let you on your way to practice the rest with the answer key afterwards. So here you have a decrease in pressure or decrease in volume, which also means that you're increasing in pressure. So let's go ahead and just write that in also. Now, decrease in volume, increase in pressure means the only thing that affects pressures are your moles of or your gases. So you're going to need to count your moles of gases. So there's 0 moles of gases here on the reactant side, and there's 2 moles of gases on the product side. So now you know where you have more moles of gases and less moles of gases. And because you're decreasing volume, you want to try to alleviate that stress by finding a way to increase um, uh, or try to go to the side with less moles of gases because there's less pressure that will be exerted there. And so your shift is going to be in the reverse direction, and that means it's this arrow. Now, how does that affect the quantities? Well, that means you're going to be making more of the reactants, and you're using up the products to make more reactants. So what effect does it have on NH3? Well, it looks like it's going to decrease that amount. So you're decreasing the amount of NH3. Now we go to temperature. So you have the stress is a decrease in heat or temperature. And so we need to definitely place our temperature where it needs to be placed. And since the reaction is endothermic, I'm going to place heat on the reactant side. Now, decreasing temperature means you want to move to try to increase temperature. So you want to move it in the direction where heat is, which is the reverse direction. And that reverse direction will increase the heat or produce more heat, which increases the temperature. Now, what effect does it have on this quantity called ammonium chloride? It looks like it's going to, because you're shifting towards making more of this, that means that quantity is going to increase. Now go ahead and pause and work through the rest of the problems the answer key will show afterwards. Moving on to the third example problem. Here in the third example problem, you're looking for how will the K constant change with each of the following stress. And we talked about this earlier, where K constant is in fact going to only change if your system is changing temperature. So K constant is temperature dependent and only temperature dependent. So you can change the volume, change the pressure, change the temperature, change the concentrations. It's not going to change. K constant will not change. So if you go through and comb through each of these examples, nothing's going to change your K constant except for letter B. So this is NC. NC means no change. And so all the other letters are no changes. So the one that is really the focus is temperature. So to know and what temperature is dependent on is whether the reaction's endothermic or exothermic. So in the forward direction, it looks like it's exothermic, okay? In the reverse direction, it's endothermic. So how K will change is if you increase temperature, according to Le Chatelier's principle, you're going to try to absorb that heat. So it's going to reverse. So this is going to be a reverse direction. I shouldn't put the arrow there because it actually looks like it's a certain direction of shift. So it's going to reverse itself. And that means the reaction is going to go fast in the reverse direction, so this way, to absorb that heat. Now, upon reversing, that means more products are forming. And what KQ is based off of is products over reactants. It's a concentration of products over reactants. So if you have more reactants, you're reversing the reaction, which means you're forming more reactants and also lessening the products. What happens to your K constant? It actually is decreasing. And so your K constant is going to resulting in a decrease. And that's the only thing that will change K in the end. So the reaction reversing will decrease your K constant.